Good afternoon. That's the hardcore, huh? The hardcore who are till the last minute here, which is important. So I just had a problem with the projector, actually. I made the problem. So we're going to work from this screen here, huh? For the moment. The last time we spoke about the marriage between the enthalpic effect, which is the enthalpy, and the entropic effect, which is the entropy. And we have seen that the direction of a chemical reaction, if a chemical reaction is spontaneous or non-spontaneous, depends very much on that new state function, the Gibbs free energy, delta G not at standard state. The Gibbs free energy, we have decided, the Gibbs free energy is delta H0 minus T times delta S. So this is our enthalpy here, and this is our entropy, change in entropy. And if delta G is negative, that means if delta G is negative, then the reaction is spontaneous. So you calculate the change in Gibbs free energy of formation of your reactants, take the sum of those, don't forget the stoichiometric factors, and you also calculate the change in Gibbs free energy of the products. Don't forget the factor, the stoichiometric factor. You take the result that you get for the products minus the result that you get for reactants, and with this you get delta G naught. That means if this is a negative number, that reaction as you have written it will proceed spontaneously. It will go like quickly. No, that has nothing to do with it. It doesn't tell you if it goes quickly, but it will go. Quickly you will get from kinetics, but it will be a spontaneous reaction, okay? And if this is equal to 0, then the reaction is in equilibrium. That means the universe doesn't care if there's reactants or products, they go back and forth in each other, and with this delta G naught is 0. And we talk about this more today. And if delta G naught is larger than 0, then that reaction does not go at all. Okay? It's not spontaneous in the direction that you have written it. That does not mean that it would be spontaneous in the opposite direction. Because it's highly likely that it's spontaneous in the opposite direction. And so we have then discussed 4 cases. You see, there's the temperature here, and there's the change in entropy, and here's the enthalpy change. And this can be negative or positive, and this can be negative or positive. And we had 4 cases that delta H is positive, and delta S is negative. Delta H is positive, and delta S is positive. That is the next case. And there's delta H is negative, and delta S is positive, or delta H is negative, and delta S is positive. Did I say positive? Yeah. So these 4 cases. And you see, this then depends on the temperature. This always has to be negative in order for the reaction to be spontaneous, and you can play this through yourself, and we will do this actually right here now. We have a reaction, and this was the dissolution of potassium in water. You remember that we looked at these elements here, lithium, sodium, and potassium, and we put them in water. They were exothermic reactions. We can say exothermic was negative, and exothermic is negative, and then you can say here you have a solid, you have a liquid. This is a solid, there's a liquid, and a gas. So you have a solid and a liquid, you go to liquid and gas. So now you can sort of get an idea of what happens to the entropy. Does the entropy increase or decrease? That's the question you need to ask yourself. You go from a solid and a liquid to a liquid and a gas. Does the entropy increase? Yes, of course it increases. So it's positive, the change in entropy. And with this, delta H, and delta G is H, this is negative, and this is positive, delta S, it increases, so this is minus, this stays negative too, so it is negative. That would work at all, delta G is negative, it's spontaneous, and it would work at all temperatures, okay? Now the next reaction we have looked at, we did that. You have water, liquid water, and you have oxygen, and you have a liquid and a gas, you make a liquid. So this is less ordered, this is more ordered. So this I have to tell you because you don't know that. If you look it up, you know. This is an endothermic reaction, so you need to put in energy, and we have said that the order is increasing or decreasing. The order delta S, the change in entropy, so the entropy gets smaller, okay? The entropy gets smaller, and with this, here we go from liquid and solid to gas, the entropy gets larger, more microstates, more disorder. And with this case, you get more order. The gas suddenly is only a liquid here, and this was liquid, so this is a wash, but the gas also is a liquid. With this, you have it, the entropy decreases, and this would, if this is positive here, and this is negative, so this is also positive. This is positive, and this term becomes positive. What happens? Delta G naught is what? Is that reaction spontaneous? No, of course not. And so we said, if this is not spontaneous, then this one must be spontaneous in this direction. And we took H2O2, hydrogen peroxide, which was used in the old days, it's still in many of the products you use to lighten your hair. I don't like my hair, it comes with light by itself. But some people, they would like to have blonder hair, and as you called people in the old days, hydrogen peroxide blonde, actually, superoxide blonde, you called them. And so this is, it was used to bleach hair, that's also disinfectant and many other things. So when we take H2O2 and we use the catalyst, manganese, there was a catalyst, it was not really partaking in the reaction, it was just a catalyst to foster that reaction. We had steaming water, okay, which is water vapor or gas, and we had oxygen. The oxygen, of course, you couldn't see, but I breathed it, I did breathe it in, and with this I became much more invigorated. And the steaming water you had seen, it was this column, it was here, that column of steam came up here, okay? Now, so it went in the opposite direction. And then we have aluminum bromide, and it's a solid, makes a solid and a liquid, solid and liquid. So let's see if we are right. So this should be the entropy, I don't know, okay? You need to look this up, what the change in entropy is. So in this case, it's positive, but the entropy, what is a solid? Maybe I'm not wrong, a solid and a solid, so the entropy should be increasing, isn't that right? So it should be increasing, it should be also positive. Yes, it is, okay? It doesn't work always like this, but this is a pretty good indication that the entropy increases here. So this is positive, and this is positive. So then, in order for this to stay negative, this term here, the T times delta S, has to outweigh, delta S is positive, and this is positive, has to outweigh this term here. With this, you have to have high temperatures. It will be negative at high temperatures and positive at low temperature. If you do high temperatures, it goes this way. But if you do low temperature, like room temperature, we're doing it this way. So this way it's spontaneous, and let's look at that reaction. Karen has aluminum foil here and bromine liquid. Let's give it a little time here, and let's see what that reaction does. Can you turn the light down a little bit? Okay. Focus. So there it is. You don't see much? Have you turned that light off and you see it really? There you go. All right. Is it an exothermic or an endothermic reaction? You see that? Isn't that beautiful? Beautiful. Okay. That must be an exothermic reaction. Thank you very much, and thank you up in the booth. Good work. Good work, Alicia. Okay. So now I'm going to put this back on here without screwing it all up. And so you see, we did it in this direction. And of course, this was endothermic in this direction. So it's got to be exothermic in the opposite direction. All right. So the last one we did, this was our last experiment. It was, you had magnesium solid and solid carbon dioxide, dry ice. This is a solid, this is a solid, and this is a solid, and this is a solid. So you can't, it made magnesium oxide and carbon. And so here you can't really say, just by guessing, what the change in entropy is. I can tell you, when you calculate that it's an exothermic reaction, it's negative. And the change in entropy, you have two solids making two solids. So the heavier solids, the heavier the solid is, the higher the entropy. Remember that. The heavier the solid is, the higher the entropy. Okay? So what you get if you calculate this, there's an entropy decrease, actually, supposedly. And so with this is negative. So this is negative here, okay? And this is negative, so this becomes positive. So if I have very high temperature, this positive term will outweigh this term, and delta G will be positive, so it will not work. So this only if I have, this is a very small term, okay, because it's positive, and it's smaller than that term, then, yeah, it's smaller than that term, then it would work. And this only does, as you can see, at low temperatures. And this is what we did. At low temperatures, it worked. At high temperatures, it doesn't work. And you had the yin and the yang of chemistry. So you had fire and ice. I think this is one of the coolest, no pun intended, coolest experiments there are to show for you. So you had this carbon dioxide magnesium lamp here. So let me see, and I just went through this. We have that reaction, carbon dioxide and calcium oxide makes calcium carbonate. And you see, you can say you have a gas and a solid. You have a gas and a solid. So, and you make a solid with this delta S0 is negative. It gets more ordered. This is 200 joules per mole per Kelvin, delta S0. And the reaction itself is exothermic in this direction. It gives off 200 kilojoules per mole of heat. So now I'm asking you, for what temperature range is the reaction spontaneous? Is it smaller than 1,000 degrees? Or about equal to 1,000 degrees, or larger than 1,000 degrees? For which temperature, for what temperature is this a spontaneous reaction? Give it a good thought, and then try to answer this, please. All you have to do is use that formula here. And so what is delta G naught for spontaneous? It's negative, smaller than 0. That everybody knows by now. That's actually arithmetic, okay? Okay, that's not what I had hoped for. But, so, what can I help here? So first of all, what's the temperature? That temperature is in what kind of units? In Kelvin, because this is Kelvin here, okay? All right, so you have to see when is that negative here. So you have to just put that in and play with T. And just put in T smaller than 1,000, larger than 1,000, or 1,000, and then tell me when delta G becomes negative. And I think everybody should get this right. At least that's what I hope for. So please discuss this with each other. There's quite a bit of discussion necessity here. Come on, let's wake up. Let's discuss it. Last effort before there might be another lecture for you, though, maybe, before the midterm. 2 more lectures. See, everybody thinks they're the most important. Okay, I don't think that, though. It's just it. No, it's a week after. It's a week after. No, I was just asked when the next midterm is. That's a week after the break. Okay, that's the 6th or something. Or the 9th, yeah, the 9th. It's always on a Monday. No, but the homework is due on Monday, April 2nd. But this is the homework. There's no homework we give you on next Monday. You had 2 weeks to do your homework. So you could have done this already, put it in. And so I don't give you homework over the spring break. If you haven't done it, of course, then it's homework over the spring break. Or you can get up at Monday morning at 4 o'clock and then spring break is over. Yes, I'm so happy. Okay, good. That's an essential thing. So you need to be able to make this reasoning here, okay? All right. So calcium oxide plus CO2 gas gives solid calcium carbonate. That's an exothermic reaction. The enthalpy decreases because you have more order. With this here, T times delta S, it must, if it's delta H, that happens at 1,000 degrees, okay? So, but you need to have the one larger, so that needs to be negative. That means T has to be, if T is above 1,000 degrees, and T is smaller than 1,000 degrees. So what happens if T is above 1,000 degrees? You have delta G naught is 0. Nada. Nilch happens, okay? So that's non-spontaneous. And if T is smaller than 1,000 degrees, then you, of course, will have a negative value. Delta G naught will be 0, smaller than 0. And with this, the answer was smaller than 1,000 degrees Kelvin. So today, we're going to talk more about equilibria, and we look at equilibria in terms of free energy. And if you have a system in equilibria, delta G naught in equilibrium, delta G naught is 0, okay? So the universe doesn't care if they're reactants or products or reactants. And actually what happens in an equilibrium, in a chemical equilibrium, products go back to reactants and reactants go back to form products again. It goes back and forth and back and forth and back and forth. It's not a static equilibrium. It's a dynamic equilibrium. Chemical equilibria are dynamic equilibrium because you have all the motion. But the universe doesn't care if it's products or reactants because delta G naught is 0. So let's look if we have an equilibrium. We have reactants A moles of reactant A plus B moles of reactant B. And we are making C moles of reactant C, of product C, and D moles of product D. All right? That's a chemical equation. So this shows that it's not an equilibrium. Okay? This also wouldn't be an equilibrium. It goes back and forth and back and forth and back and forth and back and forth. Stop. Aha, it's an equilibrium now. Okay? We know not that delta G naught, if this is an equilibrium, if I write this here, that's an equilibrium reaction. If I look at the delta G naught, and I said this already, we say that the delta G naught is 0. Okay? Now, you can write For example, this would be, you have a phase change. You have a liquid going into a gas. This would be water, goes into a gas. Where would that happen? Where would that be in equilibrium? At the boiling point, exactly. At the boiling point, and it will be in equilibrium. So the universe doesn't care if it's water gas or water liquid. The gas condenses and the liquid evaporates. And it goes back and forth and back and forth. Of course, if you keep putting in energy, then it will eventually leave the system. But if it's in equilibrium, then the delta G is 0 for that. So you have a gas phase equilibrium. And so equilibrium, see, there's the PI. Okay, let's see what this is. Now, equilibria are pretty boring, actually. So this is, welcome Beijing. This is nitrous oxide, NO2, or partially also Los Angeles. So NO2, this is a brown gas, and I have this in this closed flask here. NO2 dimerizes to N2O4. We had this in the chem quiz, actually. And N2O4 is colorless. So there's N2O4 goes to NO2, N2O4, NO2, NO2. I don't see nothing, okay? So that's an equilibrium. Pretty boring, isn't it? Nothing is happening, okay? And so that would be a gaseous equilibrium. So you have a dimerization of NO2, and this is an equilibrium under certain conditions. And then you have an aqueous equilibrium, where you use the concentration. So you have, this is a shortcut, an acronym essentially for acetic acid that chemists use. H is the proton, and AC is for acetate, acetic acid. And this is in water, that proton goes from here to here, makes H3O plus the acetate minus ion. So this is dissociation. It's essentially an acid-base equilibrium. We will learn about this. So when this is in equilibrium, then delta G is 0. That means there are certain concentrations where it is in equilibrium. And this is a homogeneous equilibrium because you have a liquid, and here you have a liquid, and that makes a liquid and a liquid. So there's no change in phases. That's called a homogeneous equilibrium. If you have a heterogeneous equilibrium, you have, so for example, dissolved silver ions and dissolved chloride ions. When they meet each other, they precipitate. They form silver chloride solid. It's a solid, and I think you will even do an experiment like this in the lab. So that's a heterogeneous equilibrium. And you're not on the phone, are you? No, okay, good. All right. Good. So if we look at this mass action law, we can say the following. We make a reaction quotient. We call this quotient Q. Okay? And Q is, we say, this is the product, the concentration of the product, divided by the concentration of the reactant. Product divided by reactants. So if I have this all at standard condition, standard state, what would be the Q be? So everything would be at 1 atmosphere on the left side, and everything would be at 1 atmosphere on the right side. And with this, it's all 1, okay? So that would be, the product would have some concentration of 1, this has a concentration of 1, so Q would be 1, okay? At standard state, what is standard state? 25 degrees, or 298.15, and 1 atmosphere of pressure, okay? So that's here, 1 atmosphere of pressure, that's what we have about. And so I can say, if I have this in solution, I take the concentration, and then I make these square brackets, the concentration of product C to the C's power, that's the number of moles, I put them as a power here, times the concentration of product D to the D's power, and the reactants is the same. I have the concentration of reactant A to the A's power times the concentration of reactant B to the B's power, okay? And if I have this here, the concentration, if I let's see that's a solution, and it's standard state, that's a hypothetical condition, standard state. There would be, everything would be at 1 molar. 1 molar products, 1 molar reactants. Of course, it never happens. But this is how we compare our thermodynamic functions, that we have a system that we can relate to in our calculations. So what would be Q again? If the concentrations were everywhere 1 molar, what would that be? Would be 1 again, okay? So now, let's see, we have put A and B together, and we don't have any C or D, all right? So obviously the reaction is not in equilibrium. Now it makes C and D. And let's say we are either very fast or the reaction is slow enough that we can take samples. How much A and B do I have here? How much C and D do I have here? And at every point of that reaction in time, I can make that reaction quotient, okay? That reaction quotient, because the reaction is going on. So this here will, if it goes, this will become smaller here, and this will become bigger. And eventually, you will have an equilibrium. When the reaction has reached equilibrium, then the concentrations will be not the same, but they come to a certain equilibrium concentration set. And at equilibrium, then we call this constant K. Q is, of course, at the beginning of the reaction, but it's not in equilibrium. And if you talk about standard states, then it would be 1. But when it's in equilibrium, it's a constant. And you can look up these constants for how the reaction is written. They're in books. Just like you have your standard enthalpies of formation, you look up equilibrium constants for all kinds of reactions. And I show you later how you can actually infer this or calculate this through thermodynamic properties. So you don't have to measure them all directly, but you can determine them. But let's assume that they are measured, and you look them up. They are equilibrium constants for acids and for bases and for all kinds of reactions. They're in big books or now in big computer databases. And you look it up and you say, this is a fixed number for that reaction. And it has to reach that fixed number here. So that means there has to be a relationship between the products, products and the reactants to reach that number. Okay? Of course, there's an infinite or a very large number of possibilities that we can have to reach that number. So if Q is smaller than the equilibrium, so Q is the value, we measure that value, what the value for Q is while we go at the reaction, what happens? This is smaller than K. If Q is smaller than K, what does that mean? Q is smaller than K, so we have too much of A and B, isn't that right? We have too much in the denominator. Or we don't have